Ladies and gentlemen, welcome to the second day of IALA 2021. I hope you're enjoying the sessions as well as the great platform with specific features. If this is the first time you're checking in the live broadcast, welcome. My name is Pauline de Wilde and I will be your general host for the next couple of days. And I will announce all the chairs that will host the different sessions. Yesterday, we sent out a push notification for the poll. How many unique connections do you think has been made on the first day? Well, most of you thought it was less than 50, but there were more than 200 unique connections made, so that's awesome. And the chat messages between the more than 200 participants was almost 900. So we would like to say, stay active on the platform and make sure that you connect. Today, we will have 3 sessions for you. The first is managing risk, the second, anomaly detection and decision support, and the third is embracing e-navigation. I think it's time to start. We're about to start with the first session. And please make sure that you post your questions for the presenters in the live chat, because we have our own host at the chat desk, Mr. Maarten Bervoets. Maarten, are you ready for some questions?
I'm ready for the questions.
And we have dial-in presenters and pre-recorded presenters. Yes. What do we do with the questions for the pre-recorded sessions?
We will have them in the chat and we'll ask the presenters to answer them, all those questions in the chats.
Perfect. Thank you, Maarten.
Okay, will do.
The first session will be chaired by Mr. Trond Ski, Senior Advisor, Norwegian Coastal Administration. Mr. Ski has served with the Norwegian Coastal Administration for more than 16 years as a Senior Advisor and a subject matter expert on vessel traffic services and maritime safety information. He is the acting chair of the IMO Enhanced Group Call Coordinating Panel, the chair of the Operations Working Group of the IALA VTS Committee, and the vice chair of the IHO Worldwide Navigation Warning Service Subcommittee. Are you there, Mr. Ski? Yes, you're there.
Yes. Good morning, Pauline.
Good morning. You are a busy man with all those chair functions. Do you have time for us today?
Yeah, let's hope so. Yeah, of course I have.
Yeah, thank you for being us. Have you enjoyed some sessions already? Were you possible?
Yes, I have. I followed all the sessions yesterday. So yeah, that was very interesting indeed.
Nice. Well, I give the floor to you so you can start with the session and the introduction of the speakers. Enjoy.
Thank you, Pauline. And congratulations on your achievements, hosting us through the first day of the symposium in an exemplary manner. And I must, I must admit that I'm a bit envious looking at the view out of your studio window, which indicates that spring has arrived in Rotterdam. Up here in the middle of Norway, we are still waiting for the winter to let go.
We had snow yesterday.
Oh, you had?
Yeah.
Oh, we have snowstorms outside right now, so that's, yeah. But there is, of course, no greater way to wait for warmer weather than to participate in this well-composed symposium. So by that, let's start the first of today's 3 sessions. So good morning, good afternoon, and good evening to you all, and welcome to the first session of day 2 of this symposium. At this session, managing risk is on the agenda. With this, we are entering into the core business of the IALA family. Managing risk, or the reduction of risk, if you like, is our profession. We have 3 speakers under this agenda item, all focusing on the use of data and technology within risk management. As highlighted yesterday in the welcome speech of the Dutch Minister of Infrastructure and Water Management, we are still learning how data can contribute to make the maritime transport safer. But we are, of course, using technology in a larger scale today than ever before. In this session, we will learn about the way to use AIS data, algorithms, and artificial intelligence within risk management. And we will get a better understanding on how the IALA toolbox can support the risk management process in waters with very complicated traffic patterns. But before we start, I would like again to remind you all that you, as a participant, can ask questions via the chat, and that the chat will be moderated throughout the session. So our first speaker of the day is Mr. Takahiro Kato from the Japan Coast Guard. And the theme is analysis of AIS data for real-time risk detection in maritime traffic. Lieutenant Commander Kato has since April 2020 been Section Chief in the International Affairs and Engineering Development Office of the Administration and Planning Division of the Maritime Traffic Department of the Japan Coast Guard. His scope of activity is development of aids to navigation systems, including VTS. Mr. Kato is a graduate from the Department of Mechanical and Aerospace Engineering at the School of Engineering at the Tohoku University. And by that, Pauline, let's focus our attention to the presentation of Mr. Kato.
Yes, absolutely.
Hi everyone, it's good to see you all here. In today's presentation, I'm hoping to give you an overview of analysis of AIS data for real-time risk detection in maritime traffic. I would like to start by talking about contents of this presentation. Today's presentation is divided into 4 parts. I'll start with talking about background with analysis of AIS data and development of anchor tracking early warning system. Next, I'll talk about anchor tracking early warning systems concept. I'll show you demonstrations and experimental result. And finally, I'll conclude this presentation. AIS is a powerful tool to prevent collision accidents between ships. It automatically exchanges a variety of information between ships and between ships and land. For example, ship's position, course, ship's name, ship type, and so on. JCG use AIS data for BTS, and JCG accumulate the AIS data of ships. JCG has developed 2 systems for real-time risk detection by analyzing the accumulated past AIS data as big data. In recent years, JCG has developed 2 systems. The first is an anchor tracking early warning system, and the second is predicting ship collision risks. This presentation will introduce the development of anchor tracking early warning system. Let's start with the background of this technology development. In recent years, typhoons have become larger and more frequent in Japan. In September 2018, a typhoon struck Japan, causing an accident due to anchor tracking. As a result, the function of an offshore airport was suspended for 14 days. In addition, there have been many other ship accidents caused by anchor tracking. Accidents caused by anchor tracking are increasing in Japan. I will explain the current method of monitoring anchor ships by BTS. A guard circle is set up around the anchor ships to be monitored. When the ship deviates from the guard circle, an anchor tracking is detected. However, when deviating from the guard circle, information opportunities may have already missed. On the other hand, narrowing the guard circle increases the alarms. Therefore, the determination of anchor tracking is highly dependent on the experiments and skill of the BTS operator. The purpose of development is to provide timely and appropriate information to prevent anchor tracking accidents, and at the same time to reduce the burden on BTS operator related to monitoring anchored to ships. The guard circle method takes into account the length of the ship and wind speed, but it does not take into account the actual speeds of ships or the time it has moved. So we focus on ship's characteristic swinging motion of anchor tracking obtained from AIS data. I will now explain typical anchor tracking pattern in a way that the pattern leading to anchor tracking can be explained as follows. State A is normal state. Ship is in swinging motion. State B is transient state. Anchor slides downwind gradually, but ship keeps swinging around. State C is anchor tracking state. Ship is swept downwind at constant speed and posture. We focus on the characteristic motion of ships leading to tracking anchor, and conducted a cluster analysis of AIS data for the past 10 years by the following 5 motion factors. As a result, we obtain results that can be classified ship's motions into 8 clusters, and we scored each motion according to degree of risk. In this section, I will explain the outline of using the ship's motion to detect anchor tracking. The concept is moving continuously in dangerous condition is risky. So define the evaluation value E as degree of danger multiplied by distance moved in that state. When the accumulation of the evaluation value E exceeded the threshold, we detect the ship is anchor tracking. We developed an emulator with the above-mentioned algorithm. The center window shows the movement of ships by AIS data, including anchoring ships. Ships marked in red are alert of tracking anchor, and we optimized parameters by analyzing past 7,500 anchor monitoring ships. I would like to show you the demonstration. This example is from a stormy day in 2015. The following figure shows the ship's trajectory and elapsed times in this demonstration. From 0 minutes to 30 minutes, ships swinging around. It's in normal state. After 30 minutes, anchor slides downwind gradually, but ship keeps swinging around. It's in transient state. In 45 minutes, a new method detected anchor tracking. In 48 minutes, the ship deviates from the guard circle. The guard circle method detected anchor tracking in this point. After the ship deviates from the guard circle, ship is swept downwind at constant speed and posture. It's completely anchor tracking state. So it shows that tracking anchor can be detected during the transient state leading up to tracking anchor. And new method can detect faster than guard circle method. However, problems also exist. False alarms may occur depending on the state of ships. There is a trade-off between early detection and false alarms. Therefore, further optimization of various parameters is required. So, in order to solve those problems, we plan to continue the verification process at the BTS Center. I would like to conclude my presentation. This presentation introduced analysis of AIS data for real-time risk detection in maritime traffic. In particular, development of anchor tracking early warning systems. By analysis AIS data, JCG developed a new method of detection of anchor tracking. And anchor tracking can be detected during the transient state leading up to it. Anchor tracking early warning systems can be useful for early detection by BTS operator. In the future, we will implement this system in BTS centers. Thank you for your attention.
Well, thank you, Mr. Kato, for your interesting presentation on how to develop the development technologies and the use of algorithms and how they can improve the detection of potential risk of maritime accidents like the dragging of anchor, and also outlining how the Japan Coast Guard use such technologies. So again, thank you, Mr. Kato. Our next speaker is Jody Daniels from Saab, giving us an insight in the use of artificial intelligence to predict long-term collision risk. Jody Daniels has a Bachelor of Science and a Master of Science in Business IT. He has a postmaster degree with honors in artificial intelligence research. He has been active in the area of artificial intelligence and machine learning from the start of his career, and he is always looking for new and exciting opportunities. At Saab, Jody Daniels is an analytics translator of data science and artificial intelligence, aiming to contribute to a more sustainable future by improving the safety, efficiency, and environmental responsibility of the maritime sector. And by that introduction, let us focus our attention to the presentation of Mr. Daniels.
Hi, and welcome to my presentation about predicting long-term collision risk. My name is Jordi Daniels, and it's getting busy. Maritime traffic is still increasing over the last 20 years by 300%. Still, in the whole world in trade, 90% of all cross-continent trade is carried by sea. And this is bringing some implications or some complications in maritime traffic. One thing is, as it's getting busier, more vessels are traveling, and also larger vessels are traveling across sea. And while that may not be a problem for oceans and seas, it is a problem in coastal areas and ports. Because as that is increasing, the amount of ships and the size of ships, the size of ports is very difficult to also increase at the same rate. And bring into that mixture as well that more sea structures are being built than ever. Here in the Netherlands, we are building massive windmill parks that even narrow the amount of waterway down more, which brings up the quantity in ships and also the density of waterways, which could lead to more complications and collisions, which is one of the problems that we're countering here. Now, I do not have to tell you about the negative effects of collisions, which are terrible, of course, but also potential collisions, so collisions that never occur at all, have a massive negative side effect, whether that is financial, environmental, by the amount of extra CO2 emitted, or just stress of captains and also other personnel involved. So the problem is quite big, and the amount of casualties is big as well. While still the biggest problem of the biggest casualty cause is still the loss of propulsion power, which accounts for 22% of all casualties. Collisions account for 13%, and two others, contact and grounding, account for 17% and 13% respectively. They add up together to 44%, and they all have the same problem. They all have the same problem, which is navigational nature. So problems with the navigation of ships. And that is something that we would like to counter here. And while the amount of casualties is only 13% for collisions, the amount of fatalities is way higher for collisions. Because when collisions do occur, they are very drastic. And that's why we want to do research on this and try to predict them. But there's another problem, a small problem, which is very heavy impact, which is the data. So AI can work in all sorts of ways. We can use inductive method or deductive method. But there's a problem with the data. The scarcity of data is massive. There's just a lack of observations, because while collisions are terrible and they happen quite frequently, in order to do proper machine or deep learning, there's actually not enough data. But we can move from a different way as well. We can make observations, we can recognize patterns, and then make a lot of assumptions which we guard with expert opinions in order to make hypotheses. And that's what I'm going to present right here, and the theory of how to do long-term collision risk. But why should we even use AI? That's a question I get asked so many times, and the key is in the observations and the pattern recognition. AI is just very strong in this. It can understand billions of rows of data And don't be alarmed, a billion rows of data is what a port produces annually, for example, in our systems. And it can recognize patterns in all those billions of rows of data. So the method of prediction that I'm using is the following process. It's quite a big process. We're moving from predicting the destination to analyzing the route, to predicting the fairway, predicting the speed, calculating ETAs for all positions, correlating paths and ETAs, and then predicting collisions. But I want to highlight just 3 process steps, which are predicting the destination harbor, predicting the fairway, and predicting the speed. And that is what I'm going to talk about now. So first, predicting the destination harbor, which is a classic classification problem. We use the following features for that. And that's actually funny because there's a story attached to this. I was once in Rotterdam talking about collision detection, and an operator triggered me because he said, with just the name of a ship and the way it was sailing through the port, he was able to tell for every ship where that ship was going. And that triggered me into thinking, well, maybe an AI or machine learning application can do this as well. So we actually built that. And we do not use name as of yet because of data regulation items. But it is something that I want to use. We do use MMSI, but we've anonymized that. And from MMSI, we also thought maybe we can use continents, but that does not help that much in prediction. As you can see right here, the feature importance is very, very, very low. So that's it for predicting destinations. We are actually quite good at this right now, but we need more data. That is the key. We need more data. Now, the second step that I would like to explain is how we predict fairways. So when you know where a ship is going, what the destination is, you still need to know how it is going there. And we use quite cool algorithms for that. One is called the evolutionary algorithm, and with a genetic approach, where we actually train a model to evolve over time with all the routes implemented one at a time into the algorithm, which you can see here, moving from stages to stage. On the left, a very, very wild evolutionary algorithm still. In the middle, a bit better with box plots on what routes are normally taken. And on the right, we are actually able to predict the curvature around corners, which is very difficult to do. And this is also a classification or clustering problem that we worked with. Now, the final part that I would like to explain is predicting speed and how we do that, which is a typical regression problem. And it's very, very difficult, even though it's a very low dimensional problem, which should be relatively easy. Speed is hard. It took weeks or months to understand how difficult this actually is. But predictions are getting better. As we input more data and we are able to recognize more of the history of the data, we can get numbers up to 88% accuracy for some routes in which where a lot of ships travel. And as you can see by these box plots, with the colors representing the interquartile range, for some routes we are only off 5 seconds when you take the IQR. But this is also heavily influenced by the amount of data. And that is the key in all these 3 process steps. We need more data. But we do have some results, and we're getting quite close. So for example, these 2 ships moving through the Botlek area, we are able to predict 14 minutes in advance where they are, quite accurately, up to some meters difference. And it actually works. So this is not simulated data. It is just real track data simulated to have a collision. And also this track, so 2 ships moving from Nieuwe and Oude Maas, 11 minutes in advance we are able to tell that they are on a collision course using our predictive collision risk models. But it gets a little bit more complicated because we do not, it does not matter whether you take 2 or 3 or 4 tracks. So in this example, we take 4 tracks. And you can see in the first image on the top left the 4 tracks are coming together. In the second image, you can see the first collision occurring between the first 2 ships from Botlek and Oude Maas. In the third image, you can see another collision occurring just before the entrance of Botlek area. And in the fourth image, another collision, which I also highlighted in blue, on the Nieuwe Maas. So it does not matter how many tracks there are, we can predict collisions for them. And this is also the strength of this program. So operators and captains are extremely good in what they do. They are highly skilled people. But AI can help them in situations where they just cannot predict around the corner and help there. And that is also what I would like you to keep in mind. While the captain has this view, the operator has this view, AI has this view. AI can analyze so much data using trained models, up to thousands of rows at the same time, in real time, without any effort at all. And that is the strength of AI. We can take a look at the whole situation, just less in depth, because we have the captain and operators doing that, and they're extremely good at it. Now, for my final slide, I would like to take a quick look at future research, because this is the exciting part. I mean, what are we going to do now? We have these results, and now what? So we are able to process more and more data. I mean, computational power isn't a problem anymore, storage isn't a problem anymore. So we are going to use more data. We are also going to build new environments in order to test our models, to train our models more efficiently, but also to be able to test with with operators and also captains and other key users in order to make sure that our software actually works and our predictions are good and are viable. Another thing that we want to implement is feedback learning. So are we able to make the models better based off of these expert opinions? And can we implement it then in the models? And then we start confirming the theory. So we're taking the deductive approach. We use the theory and we try to test the hypotheses. But we have to keep some things in mind while doing this. So we can train with more data, we can have new environments, but we should never sit on the operator or captain's chair. And that is one thing that I'm also always keeping in mind. We want them to collaborate. AI and humans can collaborate. They should not be head-to-head together, but they should think together. And while humans are very good in understanding complex situations in a split second, AI is very good in analyzing thousands or millions of rows of data at the same time. Another thing is that we should take a look into or keep in mind management by exception. So my idea is that AI does not take over the job of an operator or captain, at least not in the near future. But AI puts the captain or operator on the case. So we get more of a dynamic like this, where the AI takes all the normal cases, all the things that are predictable, and for everything that is not predictable, that is not normal, we take the operator, we take the captain, and put them on the case, because they are so skilled in understanding something, understanding complex situation in just a split of a second. And then the AI can then present the information in such a way that it increases the situational awareness of the captain or operator. And finally, what we keep in mind is silent VTS, so system-to-system communication, and of course autonomy, which is one of the biggest hypes of this, also this symposium, where ships are being built that can sail autonomously. We are also thinking of how should a system-wide approach take a look into this autonomy, and can AI help in that? So that is it. Thank you for listening to my presentation, and if you want to discuss more about the models that we use, or in-depth the data, or anything that we do or that I just showed you, I invite you to come take a look at the Saab booth, where I will be and my colleagues, and we can discuss anything you want. So thank you.
Right now in the chat, Mr. Takaharu and Mr. Daniels are available for some questions. So I would say go ahead and ask them anything that you would like to know, because they're in the chat right now. Thank you.
Okay, thank you, Pauline. And thank you, Mr. Daniels, for your interesting presentation. and giving us an insight to the research of the use of machine learning algorithms to predict the risk of collision. For people like me that can barely pronounce the word artificial intelligence, such research is certainly very fascinating. So thank you again, Mr. Daniels. The last speaker of this session is Ranjuan Kwe from the Navigational Institute of Jamai University of the People's Republic of China. She is a PhD on management science and a professor with a long-term research experience of technology applications on aids to navigation. Professor Ke has gained IALA certification as a level 1 ATON manager and have since 2015 been engaged in the IALA ARM committee. Today, she will give us an insight on the use of the IALA toolbox to support the risk management process in the very busy Xijimen Gateway Channel. So again, please remember to post your questions in the chat. And by that reminder, I will have the pleasure to give the floor to Professor Kwe. So, Professor.
Hello, everyone. Yes. Good morning, everyone. This is Ke from Jimei University, and my topic is risk management in Xijimen Channel. There are 4 parts of my presentation. The first one is introduction, and the second, IRAP application. The third, PULSAR test, and the fourth, conclusions. And then the last but not least, Q&A. First, I would like to introduce the Xijimen Channel. It is one of the biggest channels of Ningbo Zhoushan Port. And Ningbo Zhoushan Port is the world #1. It has world #1 throughput for 12 years, from 2008 till 2020. And it's an important container port also for iron and steel, crude oil and liquid, chemical product transfer, ground and coal import. And the Xijimen Channel is with high density of traffic flow. As per the requirement of IMO to Marine Safety Administration of members in respect of risk management, this research based on AIS data of Xijimen Channel, which is the main entrance, with the help of a IRAP tool recommended by IALA to discuss ship's collision probability on east-west bound and south-northbound traffic flow, and offers some advice to keep safe of channel. Further, PULSAR is applied as well to check more in detail about channel risk, obtaining wider vision from experts familiar with this channel. Then some advice given to mitigate risk of Xijimen Channel. The Xijimen Channel is in Zhoushan fishing area, and fishing boats with north-south flow have great impact on the safe navigation of this area. Such complicated traffic flow put greater pressure on ships. At the same time, there are many types of ships, and the existing Xijimen North Anchorage is relatively close to the main channel. All of the above calls for evaluation of risk and measures to mitigate risk. Here you can read the Xijimen Channel, the location of it. It is a east-west channel, but there are many ships allowed, and there are also north-southbound traffic flow. And for risk evaluation, first we would like to have a IRAP application. We take some AIS data to evaluate, and then the data shows that the traffic flow adjustment is quite high, and the float is in number style. So in the software, we applied the number model for the data. The AIS data shows that the most of the vessel is general cargo vessel with length of load 75 to 100 meter. However, there are also big vessels, such as LNG vessels, and there are tankers. After the data running, we got the result as total collision is 0.008837 instance per year. It's quite low. But after communication with pilots, the exempt area are extended. The result shows both east-west bound and north-south bound. So we can read from the graph that here are some vessels is in west and east bound, and also many vessels is west and north south bound. The traffic flow is quite complicated. Many fishing vessels. And after that, after we extend the area, the total collision increased to 0.06266 instance per year, almost 70 times as simply east-west bound. Actually, there are no accidents in Ningbo in this channel by now, but however, potential safety hazards still exist. Based on current management system, it is necessary to strengthen the monitoring and guiding load of the VTS center. At present, the 24-hour, 7-day VTS service has been provided. But when an emergency occurs, the response speed of the staff on duty and the standardization and timeliness of handling vessels are particularly important. It is recommended that duty personnel be regularly trained and assessed for their ability. And also, there are currently 18 navigation beacons in the outer channel of Shadman channel, large-scale light buoys at Shadman, and 7 steel electronic buoys with a diameter of 3 meters, and 10 radio navigation beacons. The navigation security work has been better. And the next step can be based on characteristics of north-south fishing boats in the channel and cooperated with the Marine Fishery Department to better supervise the safety of fishing boat. And experienced mariners used to keep on watch when approaching into the channel and towards terminals, which also reduce the risk of any accidents. And there are communications among stakeholders. And these communications are frequently, which we can read from PASA test later. So here comes to PASA test. This tool is used by US Coast Guard. And here we also take it for the evaluation of risk in Shadman channel. There are 4 groups, or 6 groups. There are 6 groups in PASA model. And each group has 4 kinds of factor, as shown in this graph. You can see 6 groups as vessel condition, traffic condition, navigational condition, waterway condition, and there are immediate consequence and subsequent consequence. It also showed on IALA guideline 1124. Because the time is very limited and the budget is limited, so we just took on interviewed on spot. Here, I would like to share this experience because for former PALSA, it would take a 2-day seminar. And we would like to have comments on whether this simplified method is acceptable in case. We interviewed with experts from different authorities in maritime field. And from Excel table, there are some data from previous seminars. And this graph shows the data of A value, B value, C value, and D value of each factor for 6 groups. For A value, it is the lowest risk, and for D value, it is highest risk. After putting the 15 questionnaire, return the data from 15 questionnaires, we can find that there are 3 factors in high risk. The first one is petroleum discharge, and the second is hazardous mysterious release, and the third is value of commercial traffic. These 3 factors are in high risk, and later I will give some advice concerning these 3 factors. Also, there are some factors exceed C value, which means that we should take great attention to such factors, which I showed in red here. The first one, value of small craft traffic. This is related to what I just said, that the fishing boats is, there are many fishing boats in south-north traffic flow. And the dimension, the waterways dimensions is 6.6, is also exceeds C value. And there are also traffic mix, which we have read in AIS data flow, traffic flow. There are east-west bound and there are north-south bound. Also, economic has some risk because there are the pattern and hazardous materials, I think that that's correlated. So after the LNG, LPG tanker chemical vessels are in high ratio here. So the value of petroleum discharge is very high. It's up to D value. Then communicate with the experts. There are some advice for mitigate petroleum discharge and release risk. The highest one. First one, the advice is build up oil and hazardous military instruments in the channel area and get feedback as soon as possible if there is a linkage accident. Second, assign weather sensor on buoys in the entire waterway to help large tankers and others get meteorological and hydrological information of the waterway and assist the ship's navigation. The third, increasing the checking frequency of pollutant emergency. The fourth, prepare oil pollution device in advance. And the fifth, better pilot operation. And if possible, assign 2 pilots to VLCC etc. Then, the advice for mitigate the risk of high commercial traffic flow. There are also some advice. First one, better development of another channel, which is called 调走门 waterway to distribute commercial traffic flow and release the navigation pressure of 沙之门 waterway. But it is necessary to manage the ship traffic in the warning zone. Second, supervise the fishing boats to operate in designated areas and VTS warm ships which did not obey the regulations. Third, maintain anchorage and build new anchorage to adapt to the ever increasing ship size and draft as well. And so there are some other advice as following, such as broadcasting weather forest information through AIS and such on to mariners, set up monitoring instruments for hazard materials, ships looting system and traffic separation chain, virtual agent to help vessels, especially in narrow and cross channels, maintain chargement channel as well, while set up another one nearby called 调走门 channel to distribute the traffic flow. Then we come to our conclusions. Because this is the first time that we use quantitative tool as IREP and qualitative tool as PALSA to assess the risk and mitigate and try to find some mitigate measures for risk. So here we have this conclusion. The risk management is vital for judgment channel, and the traffic flow is complicated. IREP and PALSA tools help to analyze further and more in details. The mitigation measures works. Some have been in use while others on the way. Since we have done this research in 2018, and after that, here's 2 years passed by. So there are some measures have been in use. And the third, further study is needed to evaluate coming scenario. And then after that, we can have improve some measures or have some other methods to further mitigate the risk and be more safe and come to the safer sea, safer water, safer channel. Thank you. That's all.
Thank you, Mrs. Kay.
Yes, thank you, Professor Craig, for your interesting presentation on the use of the IALA toolbox in the risk management of these GMN channels. So thank you very much. And by that, Pauline, we are approaching the end of this session. And
I will have a question. I do have a question for Mrs. Kay coming in.
Okay.
So, Mrs. Kay, thank you for your interesting presentation. We see this problem all over the world. Fishing vessels have their own rules. We sometimes see that they switch off their AIS. How can your study reduce the burden ashore when some vessels are not using AIS?
Yes, that's a problem. We do find that some vessels just switch off, or some vessels just some information of AIS, even they switch on, but the information is missing. And we are trying to communicate with China MSA that first one to supervise more strictly to help such vessels to switch on and to put in the correct information in AIS. But there should be other measures, I think, because some of the vessels, they just want to switch out of the supervisor of the regulation, just out of the regulation. We also advise that the VTS and the radar can help to detect such vessels, because radar they have some more sensors to have such vessels, to trace such vessels. And so we are trying to combine different sources of data together, and then to further to try to get more information, get more accurate, more exactly information and the route of these vessels.
Okay. Yeah, they should actually feel their own responsibility for using AIS, right?
Yes.
Okay, thank you very much, Mrs. Gay, for
Thank
being
you.
here with us today.
Thank you.
And thank you, Mr. Ski, for being a wonderful chair.
Thank you, Pauline.
Have a great afternoon, and hopefully the spring is coming to your country very soon.
Hopefully. And good luck with the rest of today's program.
Thank you. Thank you very much. Yes, this was our first session of day 2. The next session will start at 12 UTC time, so make sure that you're back. Check out the networking app, be in touch with participants, with sponsors, with you can set up meetings, everything that you would like to make the most out of this IALA 2021. I'll see you back in a couple of minutes. Thank you. Welcome back, ladies and gentlemen, at session 4 of IALA 2021. And this session will be about anomaly detection and decision support. And make sure that you post your question in the live chat so we can find the, I will get the questions over here. And I also would like to remind you that in the platform, it's possible to post a question for everyone. There are some questions there already, so it's a great way to communicate and to discuss great topics with other participants. The chair of this session is Mr. Jorge Arroyo. Mr. Jorge Arroyo has served in the U.S. Coast Guard for over 35 years. For the last 20 years as a program and management analyst at the Office of Navigation Systems at USCG headquarters, and their subject matter expert on shipboard navigation systems. And he has been a member of IALA for more than 20 years. So I'm very proud that he is here with us. Mr. Jorge Arroyo, are you there? Yes, you are.
Good day, everyone.
Good day. How are you doing?
I'm doing good here. Early morning for us, but good time to be here with you. And I'm very happy and proud to be participating in this new symposium, both for VTS and ENAV, but and new way of doing it with a moderator as yourself. So very nice.
And did you already have some new insights during today or yesterday?
I'm not necessarily new insight, but I mean, I thought yesterday was very informative, both highlighting that we've kind of seemed to have departed a little bit from that holistic approach of the definition of ENAV, which is something that is a concern, particularly at us at the ENAV committee. So I'm glad that that was brought to light early on in the symposium, and then hopefully with additional presentations that we have throughout the week, we'll find mechanisms to go ahead and bring that back to where it needs to be. So it was good to get a preview yesterday on some issues that we're well aware of. And then hopefully we'll hear some solutions to mitigate some of those issues as we go further in the symposium this week.
Absolutely. So you had to wake up early for us?
I sure did.
Well, thank you very much. And please be a wonderful chair for the next couple of sessions. The floor is yours.
Thank you. Okay, once again, thank you everyone for joining us on here, this fourth session of the symposium. This is a very unique and novel session that we're going to have here. I don't think any of us could have imagined talking about intelligence, anomaly detection and decision support all in one conversation, say 5 or even 10 years ago, about what is the realm of the possible. And I'm very looking forward to my 3 presenters presenting and updating you on a lot of the work that they're doing to progress, particularly decision support and how it can assist us in the VTS realm and assist us with collision avoidance. So speaking of collision avoidance, our first presenter today is Ms. Lena Lee. She is a professor at the Navigation Institute at Jimei University in Xiamen, China. She received her bachelor's degree from Dalian Maritime University with a specialization subject in ship automation in 1983. And her research interests include the theory and technique of intelligent traffic systems at sea and ship auto anti-collision avoidance and auto control. The results of her research obtained by her team for more than 20 years have been successfully applied to the navigation collision avoidance auxiliary decision-making system to 400,000 ton ships and above and 300,000 tons crude oil tankers in China. This decision support system for collision avoidance has been approved by DNV and CCS. So that's been a great accomplishment of her and her team. And she's now going to go ahead and tell us about how she's going to use her previous research on this and bringing what she's calling person-defined intelligent decision-making for vessel collisions, bring it to the realm of VTS. So I'm looking forward to hearing her presentation. So could we, she will not be live to go ahead and present. We have a recording. So may I ask that the recording be started at this time?
Of course. Yes.
Good afternoon, ladies and gentlemen. My topic is the development and application of ship collision avoidance technology for VTS. Contents of my topic including 4 parts. Part 1, Introduction. As you know, ship collision accidents causes great losses in human life and property and bring environmental pollution. Statistics show more than 80% of collision accidents are caused by human factors. The functions of current shipboard radar ALPA or VTS has limitations. The hazard and risk assessment is inadequate and decision-making automation is not supported. The threshold value of collision hazard evaluation is not self-adaptive and the false alarm is frequent. Look at the picture. The collision between the oil tank and Sanji and bull carrier Crystal occurred about 160 nautical miles east of the Yangtze River estuary. If navigation aids offer functions as reliable collision risk warning and automatic decision-making, many collision accidents could have been avoided. In order to reduce the collision accidents caused by navigation aids limitation and human factors, and ensure the safety of navigation, undergoing the stage of method exploration, pick up information, demonstration, and application. The research team of Jimei University with Enterprise has developed navigation collision avoidance decision-making assistance system called NCADAS and Ferry Navigation Anti-Collision Intelligent Early Warning System, short for FNAS. Here, PICAP means person-defined intelligent decision-making for visual collision avoidance. Part 2, PICAP method review. Object of PICAP is to simulate the harm process of excellent navigators' collision avoidance, including the correct assess, the danger situation, the extent of avoidance, the time to apply rudder and restore the original course, and whether the avoidance action creates a new danger. Its key technology is ship collision avoidance modeling based on geometrical analysis, ship collision avoidance decision-making based on expert system, pickup algorithms based on series models and rules, framework of pickup method and its appraisal standard is shown as Fingal. A set of pickup algorithms is core technology, and assessment criteria contain qualitative criteria and quantitative evaluation. Collision avoidance domain knowledge is formalized with 3 parts. First part, qualitative criteria, including guidelines of action to ensure safety of collision avoidance between ships by complying with CORES, ordinary practice and good seamanship in the difficult situation avoidance process, which obtained from questionnaire, expert consultation, and navigation simulator training. 2-part qualitative evaluation include establishing the model of potential collision risk threshold and dynamical optimization object function for decision-making implementation scheme. Part 3, a set of pickup algorithms divided into inertial pickup generation algorithms and pickup verification and optimization algorithms. Each part consists of series algorithms. Pickup simulation results show that pickup algorithms follow CORES requirements, follow the ordinary practice of seamen, and reflect their good seamanship, and embody the quantification, concretization, clarification, and reasonable extension of important concepts and provisions of the CORES. Figure 2 is shown as trajectory of the multi-ship encountered after using pickup algorithms on ship landing simulator. As is shown in figures, pickup has ability segmented process near and far targets, make emergency decisions for uncoordinated avoidance of target. NCADAS for ocean-going ship is firstly put into use in China so far. The NCADAS has been approved by CGS and DNV. This is radar interface of NCADAS. Part 3, innovative early warning mechanism of ship anti-collision for VTS, high traffic density in port and island waters area. In China, as you know, the threshold value of collision risk in VTS is not self-detective and the false alarm is frequent. So, the function of danger alarm of VTS is being closed in China. This greatly increases the working pressure of VTS personnel on duty, and there are heightened problems of navigation safety owing to high traffic density and limitation of navigation aids. It is necessary to construct dynamic risk assessment system. Figure 7 show the diagram of evaluation index, threshold system, and evaluation grade deviation. Hazard threshold, SDA, safety distance of approach, is divided into 3 levels. First level, SDA max, mean expectations SDA. Second level, SDA C, mean critical SDA. Third level, SDA mean critical collision distance. Risk threshold is divided into 4 levels. First level, D, mean critical risk distance. Second level, DCQS, mean critical distance of close quarter situation, and another DCQS, mean distance of close quarter situation, and last level, DID, mean critical origin risk distance. By using the relative motion geometric analysis method, hazard degree threshold based on expert knowledge is established. By geometrical analysis from Figure 8, the calculating method of SDA mean is shown in Formula 1. The calculating method of SDA max is shown as Formula 1, 2, and 3. Own SDA is divided into 3 levels. Obviously, threshold SDA is dynamical and self-adaptive. Figure 9 shows SDA's C questionnaire requires for ship crossing the target fault under different encounter situations and different water areas. Innovative early warning mechanism. First, model of ship collision hazard assessment. When the condition 4 is satisfied, it indicates that there is a potential collision risk between the 2 ships. Second, model of ship hazard alarm assessment. TIRS is defined as the optimal steering time for the ship to steer safely off the target ship with the respect of SDA max. Obviously, TIRS is a self-adaptive tool. If minimal TIRS is satisfied condition, then danger alarm is activated. Note, T-alarm is set manually or by default. Third, mode of ship collision risk assessment with 4 levels. A vector line of different colors is used and indicate different levels of danger. Figure 10 is shown as simulation of danger warning in Shanghai port. Part 4, Ferry Navigation Anti-Collision Intelligent Early Warning System. This is the water area for the Zhenyang car ferries. Owing to high traffic density, it is urgent to provide scientific and instant early warning to ensure the safe navigation of ferries. In order to provide early warning information consistent with the driver's subject risk level, the expert knowledge database by questionnaire, Table 1 is shown as safety distance clearance obtained from questionnaire part. The target ship speed is divided into 3 speed ranges. The early warning geometric model based on expert knowledge is established. Table 2 is shown as mean expert experience knowledge based model. DS is a typical situation identification parameter. Here is the production rules example. Finance based on ship-shore coordination. Its advantage is, firstly, accurate ferry collision hazard assessment threshold by taking radar, AIS, and DGS information fusion and dual radar system monitoring for identifying target shift scale and dynamical information. Figure 14 is showing us system architecture. The second advantage is the early warning accuracy and efficiency reaches 99%. Here is the show best for fairness. Fairness based on shipborne coordinating. Shipborne display terminal for daytime mode and night daytime mode. If present dangerous situation, it will pop up window to display dangerous target ship's name, speed, TGPA, and danger level, and with speech for driver, such as right ahead 3 level. Summary: the intelligent early warning system based on the new collision risk warning mechanism improves the accuracy of early warning, has a demonstration function, and a broad application prospect. In order to achieve the VTS intelligent early warning technology, it is necessary to construct the ship control parameter database to improve the early warning accuracy effectively. Thank you. Welcome to Jinmei University.
Yeah, that would be nice to go to that university, Mr. Aurora.
That would be very nice.
Yeah.
Very interesting presentation. I'd like to thank Dr. Lai for that. Thanks to IALA, I've been to Shanghai twice in my career, and it is very good to know that she's doing her research in that area, because that is the most incredible vessel traffic area that I've ever seen. So if she can make it work in Shanghai, it'll probably work everywhere. So looking forward to her progressing her research in this very important realm.
And you have a lot, you have seen a lot in the world. So you know that that's...
Well, about that, but
yeah.
What I've seen there, I haven't seen too many other places. Your port, and I'd say Shanghai and Rotterdam. If you can make it work in those 2 ports, you can make it work anywhere else in the world. Yes.
Beautiful one-liner. If you make it there, you can make it anywhere, right?
That's correct. Borrowing from our New York City motto.
I know. Okay, go ahead for the next session.
All right, thank you very much. So now I'd like to move on to our second presenter, who's also actually going to provide us additional information, because he's been working on developing trials to providing for decision support within BTS systems. So hopefully you'll be able to progress a little bit more and pass on his experience to us on what he's been doing in this realm. So looking forward to the presentation of Mr. Dmitry Rostofson. He works for Westalia, which is formerly Transys, since 2000. He started his career from a testing engineer in the development department and worked several years as a project installation engineer, and got back to research and development as a project manager. He's been involved in many vessel traffic services, as well as coastal and offshore surveillance projects around the world, and currently is the general manager of ship traffic control and management solutions, and responsible for all VTS and coastal surveillance product lines for Transys. He is also a VTS instructor in the Admiral Makarov State University of Maritime and Inland Shipping and Training Center. So with this, I pass it on to Dmitry.
Thank you very much, Jorge. Sorry to keep you pronouncing all our complicated Russian names.
Yes.
And
I prefer Transys.
Good morning, good afternoon, good evening to everybody. Glad to see you all in this great event, and greetings from Port of St. Petersburg, where I'm at the moment located. So I would like to speak a bit about our experience in the decision support development in Versala and present, let's say, previously we called Transos, now we call our company after acquisition by Versala Voyage. And we we've been always active on the VTS development. And what we are doing now, I'm quite happy to see the similar presentation from other people, because that's give me impression that we are all in the right track. So you probably, some of people here will feel some nostalgia looking at the left side of this picture, because this is about how decision support tools start to be developed maybe in maritime world, right? I mean, electronic decision support tools. This is an automated radar plotting aid ARPA, yeah, where all first CP, TCP, collision avoidance stuff was implemented. But of course, it was happened many years ago. Now there's a BTS system. They came from for a long way of evolution, and from the left side, we moved to the right side, where we built a complicated systems with a number of sensors, number of different additional tools which help operator to keep situational awareness. So if you look here on, but there are still problems. In fact, if you look at the evolution from ARPA to current modern system, you can spot maybe that many of the systems, they still have some legacy from the ship side solutions, and they build on classic ship-centered approach, which doesn't work very well in a VTS world. It's also, if you think about how the VTS evolved for last years, you can see that in fact, coverage area of the system became bigger and bigger. The number of ships in the area also increased, and it actually affect to the number of alerts and warnings appearing permanently in the VTS operator screen. And many of these alerts actually fails, and I think it was also presentation earlier this morning where people say how it can be how we can reduce number of these false alarms. And also what we can see that basically in many cases, decision support tools are based on the current information. We don't take into account any history. We don't take into account many other things. We just consider that we use current course and speed of the vessel to calculate if this is a dangerous situation or not, which is probably not very modern and current, let's say, in 21st century, right? Another thing what I spotted in our installations that it's very important to train operators properly if you would like to use the decision support tools properly. This is very critical, because if operators cannot use these tools, all what we do altogether doesn't make any sense. So how we are trying to solve these problems, in fact. You can see here, we try to build a new generation of active decision support. We call it in our internal product line AIM, Advanced Intelligent Maneuvering. So basically the idea of the system is to collect information about the vessel's history, provide some intelligence, provide sensors data, rules, and based on this, implement standard operator procedure. So operator procedure everywhere, in every VTS is similar. We monitor the situation, we identify some warnings on alerts, and we provide some advisory service to the ships, helping them to avoid this dangerous situation. So why I call it active decision support? Maybe you know IALA guideline on decision support tools in VTS. The active decision support basically the systems which can help operator to identify the problem and help operator to find the decision in every specific problem. So you can see how this system work in terms of workflow, yeah? So it consists of several steps. So first of all, we do prediction of the vessels based on machine learning. We try to forecast how the ship will behave in every specific area of the VTS responsibility. So we are focusing to make this prediction up to 30 minutes ahead, not to use dead reckon anymore. We try to make it more advanced rather than just the existing course of speed of the vessel. When we try to identify which problems we have in the VTS, how we can identify these problems, we try to follow the same way as Captain do. Yeah, we have a COLREGs, collision regulations. We try to analyze all the situation based on the COLREGs, and we try to advise the operator how we can avoid every specific danger in this developing picture. So we focus, of course, on the collisions and groundings. We cannot predict many of other things, but we're working to make them even more advanced. And of course, we are not excluding the operator from this process. Yeah, it's very important to provide the operator decision, and then operator can approve this decision, and this decision can be delivered to the VTS, from the VTS to the ship. Again, it could be old school VHF communication, or even it could be some machine-to-machine information delivered to the navigational system on the ship. So this is a simple operator workflow, and we try not to change it too much, because if we change it significantly, it will be very complicated for the people to understand how it works. It needs to be included to this existing operational procedures, otherwise it probably will not be so interesting for the people. So I try to go step by step on these steps, let's say. And first of all, this is a track predictor. Yeah, what we say, we try to analyze the traffic in the VTS area. So based on our assumptions, we need to have about 3 to 4 weeks collecting of the data before our machine learning team can do their magic. So they try to build a model. And on these pictures, on the left and middle picture, you can see actually this is our internal process, how we build the model. We build a traffic density, and on the base of traffic density, we start to predict how the vessel should behave in our areas. On the right side on the picture, you also can see how VTS operator can see this prediction. So you can see there is a standard vector come from AAS or from the radar, doesn't matter in our case. But you can see this blue dotted line. This is a prediction how the systems think this vessel will behave in this area. Specifically, this simple example, right? So this is just a traffic separation, and all the vessels behave more or less a similar way, but it could be different situations here. And as I said, we try to take into account the 30 minutes and let's say, because the 30 minutes is more typical for situational awareness. It could be shorter, it could be longer, but that's our target. What if the vessel already share with us the data? For example, share the route. We also use this into it doesn't make any sense to use the predicted routes if we have a route delivered directly from the vessel. So that's why we can use STM route, which can be delivered to us through the STM infrastructure, for example, Navalink environment. Important to say that this approach helps us to reduce false alarms, because dead reckoning is the source of false alarms in many cases. This is how VTS operators see this on the screen. So you can see this is a vessels, one vessel getting out from Port of Gothenburg, one vessel getting in. And in fact, you can see these prediction lines from every vessel, giving understanding how the vessel should maneuver in this specific area. Please take into account that if you will use dead reckon in this situation, just existing course and speed, you will get collision avoidance alarms on these anchorage areas where the vessels start to maneuver next to the anchorage. But in this machine learning track predictor, these false alarms, they will be simply eliminated. But this is a simple situation because there is just a channel here and vessel is following the channel. I would like to show you something more complicated. On the left side, you can see this is inside of river in the port of Gothenburg. You can see this is a traffic density. And there is some ferries which are coming on the different stops. They are just coming through the river, making about 5 or 6 stops in the different locations. So you can see how system predict this ferry behavior. So it's exactly give the traffic and how the ferry will go to the next stop, and then from this stop it will leave for the next stop. Okay, so now we predict positions of the vessel. Is that all? Well, not yet. On the base of this prediction, we need to build the collision and grounding avoidance system, right? Again, we don't want to follow simple ship models, right, where CP, TCP is a circles around each vessel, which give the understanding if this is a dangerous approach or not. We try to introduce more complicated system. You can see this is a safety domains, which we found as optimal for the configuration. So the safety domain consists of 3 ellipses. In fact, one of the ellipses is a cross track, one is an ellipse ahead, and basically that part of the ellipse, which is on the starboard, it's a bit bigger because this, according to Colrec, this is a more dangerous situation. So it need to be more advanced alarm in this case. So you can see it's not exactly symmetric. And of course, it's important to say that these domains, they need to be different for different ships, and they also need to be different even for different areas. For example, in the narrows, according to Colrec, the safety domain also should be narrow. Otherwise, you will have a lot of alarms when several vessels passing the narrows at the same time. And of course, it's possible to change it specifically for every target, but I don't think this is a real way forward, because if you imagine the area where you have 100 vessels, you will never have a chance to change all of them manually. So we try to automate it as much as possible. So when you have alarm in the safety domain, so you will see that the 2 vessels are approaching on the dangerous course. So what will be the next step? The next step, system will try to advise how actually a vessel should maneuver to avoid this situation. On the right side, you see one of the examples. So this is a vessel approaching from the crossing, let's say, traffic separation, where 2 another vessels sailing, and it has a close quarter situation. So on the starboard of this vessel, you have another vessels approaching. So they need to let go these 2 vessels. So that system suggests, you can see blue dash line, the system suggests how this vessel should maneuver to avoid this situation. During this suggestion, the system takes into account everything. It takes into account depths, navigational dangers. It's also taken into account other vessels. It's not only about these 2 vessels, it's about all the vessels in the same area. So again, these optimal decisions, they need to be aligned with the Colrecs, because otherwise the captain basically, they will probably refuse to follow this if it's against the Colrecs. So it could be different scenarios for different vessels. And I would say for 2 vessels, this doesn't make any sense to have the system introduced. But it's important if you have like 5 or 10 vessels in the same area, the system will give you more time to understand the situation and give you more time for decision making. So there are 2 simple examples, as I said. One of them is rule 14 of the Colrec, where 2 vessels are going one to each other head on, and that's the system how suggests to change this course and speed for both of the vessels to be on a safe side. And the second example is a crossing situation when one vessel is in a starboard to another vessel. So it suggests to change the course and go by step. We also have a bit more complicated situations. One of them is a famous image problem. So you can see on this video, this is some kind of image how the system suggests to solve this problem. I hope it will work in this virtual environment. You can see this is a bit prototype. It just show you how the vessel should change the course based on this automatic system. So the vessels are changing the course and speed, and they start to maneuver on this side. And I guess something has stuck here, maybe some video. You can see how the system suggests to resolve this task. So on the right side of the same picture, it's the same situation, but one of the vessel, which is heading to north, is basically not under command and restricted in maneuvering in the shallow waters. So the system suggests a bit different solution. Oops, sorry. Let me try to run it again. Yeah, you can see that the vessels heading to northbound, it's not changing the course and speed, but other vessels, they behave accordingly to let this vessel go. Thank you for organizers. They helped me to play back these videos properly. Okay, so how it looks for the operator, right? So this is a typical screen of the typical VTS screen where these decisions can be reviewed. So on the left side, you see this traffic situation with the advice automatically comes from the vessel. In the middle, you can see some additional information. So you can see which rule of the call rec applied in every specific case, why the situation is danger, and what is actually recommended way to avoid this. But operator, basically, it has different options. So on the right side of the screen, you can see that it could be automatic maneuver, but you can also select different other suggestions. So for example, you can play the situation in different approach. So not according to automatically suggested decision, but what happens if another vessel will let go? So what happens if this vessel should keep the course and speed as is, and other vessel start to maneuver? So you can play with these different situations, and then basically when you confirm one of these, the system will start to, you will see this advice which should be delivered on a ship. And then the system start to monitor how the vessel is following the advice. So if the vessel is not following the advice, you again receive alert from the system that something is wrong. So the advice exists, but these participants of this traffic situation are not following what you suggest to do. So what we try to do, is just like we try to give this to different users and see what they say. So we also have the same system for onboard solutions. We have the system for the VTS solution. We try to go through the class and key to make sure that we are on the right track and we comply to the IALA guidelines. So this is not some kind of compulsory certification, but more like a voluntary go to some trials and tests. We also go to a few maritime training centers and academies to try to collect the different feedbacks from the simulation environment. So it's interesting to say that people generally say that it's a good tool to help to keep situational awareness, and good tool to, in the situation, then the number of vessels are large and the area of responsibility are large, and you try to keep an eye on everything what's going on. So it can help, in fact, for in different cases, but of course it will not replace a person, never. At least I don't expect that this will ever happen in the nearest future, but it will help the people to make decisions quickly and make less mistakes. This is a very important output of this references from first pilot users. So, and in general, if we can try to summarize where you need this decision support tool, of course, as I said, if you have 2 vessels in the area and nothing more, it's not so critical. But if you have like 100, 200 vessels, this will be very useful. And it's also, the good thing is that when we use a machine learning stuff, we reduce number of false alarms and we reduce time for decision making. And one also important thing that in some countries we know that there is a problem with a number of that's the people who are working in the VTS, they are not really have a maritime background, so they can the system can help to make a right decision in this case. So we try to follow IALA guideline 1110, but now there is updates of this guideline on a recent VTS committee, but I think we are also in line with the updated version as well. So that was my conclusions. I think that what I would like to say in the end, that we are, this is part of our product line, but I think we are far away because of the mindset, because of trustness to this technologies. We are quite far away from really commercial applications. So we are looking for some people who are interested to be part of these tests and give us feedback how this system work in a VTS environment, where we have problems, which benefits we can get using these new technologies and so on. So if you are interested to be part of this testing, please let us know. We would be happy to arrange a separate conversation. And that's all from my side. Thank you very much for your attention. Stay safe, keep safe your family, and hope to see you face-to-face on the next IALA meetings. Thank you again.
Thank you, Mr. Dimitri Kostopchin. And if you are interested in those tests, please leave a remark at the live chat so we can pick it up and then we can address it to Mr. Dimitri Kostopchin. Thank you very much. And yeah, for you, the ship must go on, and for us, the show must go on. But thanks for being with us. Thank you. Thank you. And yeah, back to you again, Mr. Arroyo.
Thank you very much, and thank you, Dimitri. That was very informative. I'm looking forward to seeing that technology rolled out at all the VTSs. Our next presenter is a colleague, a longtime colleague, a longtime member of IALA. So it's a vice chair of one of the working groups in the ENAV committee. So I'm pleased to introduce Mr. Ernest Batty, Ernie Batty, as we know him. He's a founding member of IMIS Global, that for the last 20 years has focused on maritime information systems. Ernie serves as the technical director of IMIS and is the architect of MaryWeb, their flagship product. After completing his technical training in Transnet in South Africa, Ernie completed an NDP at the University of South Africa and a CIM with Oxford Brookes University in the United Kingdom. Ernie attended his first IALA meeting in 1995, which is earlier than I, and he worked for Maritime Data Systems, which were one of the first companies to produce AIS that I'm very familiar with, and now represents IMS Global and is still a very active member of IALA, as I mentioned, and we thank him for being the vice chair of our working group 2 in the ENAV committee. So with this, I'd like to ask for his presentation to be played. Ernie will not be here live, so it's a recorded presentation. So could we start that, please?
Sure.
Imagine a maritime information system that can be used to provide vessel traffic services amongst other maritime services within a single, high-performance, cloud-based environment. Consider that this maritime information system processes more than 12,500 data points per second and is accessed by an internet browser using streaming data technology in near real time using a broadband internet link. In this system, sensors including multiple radars, AISs, radio direction finders, meteorological and hydrographic sensors are connected using a variety of communication technologies that includes high bandwidth, low latency mobile broadband connections. Some of the data is shared using S63 electronic navigation charts. Some data is shared using specific symbology. Some of the data will be presented in graphical format. Some of the data will be presented in tabular format. Some of the data will be in the form of alerts because of triggered events. In addition to the sensor data, there is data that is generated by data analytics and the various decision support tools and systems that are used in a VTS. Operators can connect to the system using a range of technologies, including mobile broadband devices, or a PC using existing wide area or local area networks. Internet of Things technologies are connected to the system. As an example, several weather sensors are connected, gathering data every second. When there are wind gusts above a configured level, the operator is notified of the gust and the direction from which it's expected. Other similar sensors include visibility, tidal height, current direction, and current speed. This data provides a common operating picture, parts of which can be shared with the wider port community as appropriate. Sharing all or parts of the common operating picture can be achieved using low latency mobile broadband technologies. This allows some in the port community to have a real-time view of the port that supports their various responsibilities and interests, even when on the move. Imagine too that the Maritime Information System is a multi-tenant system that is hosted in the cloud, allowing multiple VTSs to run on the same cloud environment and simultaneously. Because it is a multi-tenant system, each VTS is completely unaware of the other VTSs and their operations. The cloud-based VTS runs in a central cloud environment that could be a private, government, or public cloud service provider platform. This Maritime Information System already exists. The rapid advancement in various technologies over the last 3 to 5 years has allowed this cloud-based multi-tenant system to become a reality. These technologies include internet-based streaming used for gaming, Microsoft Stadia as an example, microservices using software containers, the Internet of Things and its architecture and the ability to connect many sensors, mobile broadband connectivity being available almost anywhere, the sophisticated data streaming, storage and analytics tools and systems that are now available to the VTS operator. Consider that this cloud-based maritime information system deals with 12,500 data points per second, with data peaks being significantly higher and all data being processed in near real time. You may want to compare this data volume to Twitter, which has 6,500 tweets per second, or the MasterCard credit card system, which has 3,400 transactions per second on a global basis. The data is collected, stored, analyzed, and then shared. VTS operators connect to the data stream using an internet browser, and this provides access to all of the available VTS services. This raises questions as to how the systems and the operators deal with the current and increasing volume of data. Dealing with high volumes of data requires choices to be made about which decision support tools are required and what outputs are needed to allow operators to make the best decisions to ensure a safe, secure, environmentally protected and efficient operation. Just how do VTS operators deal with data volume, data accuracy, data trust, and the often resultant data days? Data volume and data accuracy concerns, trust, and data days lead to analysis paralysis that results in delayed and or ineffective decision making. We already see the high volumes of data in the maritime information systems, including VTSs. How do we deal with the accuracy of this data? Much has been said about the issues with AIS that could exist with spoofing, the playback of recorded AIS data, and the sending of AIS messages that can affect the operation of AIS within a specific maritime area. To have an accurate AIS data stream, each AIS-centric message needs to be analyzed in near real time. With more than 190 AIS-centric messages used in a comprehensive maritime information system, this is a significant and complex task. Typical analytics will, for example, check that the AIS data complies to the applicable technical standards, that the AIS message is expected from the source that sent it, and that the AIS message fits the context. For example, the rate of turn is within the bounds of what would be expected for the size of the ship that is transmitting the AIS data. Although data analytics does not guarantee perfect data, a significant portion of suspect data can be tagged and then either removed or used with some precautions. For the operator to be comfortable, making data-based decisions, the operator must trust the data. With high volumes of data from many different sources, being able to establish a time-stamped audit trail for each message that is received, processed, stored, displayed, shared, and or passed on to a third party is imperative. By way of an example, when a vessel enters an area where there are under-keel clearance constraints and the profile of the waterway has been carefully mapped, taking into account tide, currents, and the speed of the ship concerned, the location of the ship at any point in time, accurate to within a second, could be important. So of critical importance, before using data in decision support tool, the data must be trusted. Questions regarding data accuracy are often asked days afterwards. Consider when a soulless vessel carrying a Class A reports its position, speed over ground, and rate of turn using AIS. When was this data acquired by the AIS device? When was the data transmitted? When was the data stored and then displayed along with the other data on the operator's display and then streamed to the decision support tool? This is an interesting and often difficult question to answer when posed by the operator. To answer these questions with a high level of confidence requires a detailed audit trail, an understanding of the sensor and its operational parameters, understanding of system latencies. Once the data trust has been established, we need to deal with data days. Data days is a form of information overload when the users of a system are attempting to consume too many metrics, dimensions, charts, reports, and similar information all at the same time. When you see the audience's eyes glaze over during a data-intensive presentation, or when they review a complex dashboard, you're probably seeing the effects of data days. The human brain can only consume so much information before becoming compromised. In 1956, psychologist George A. Miller found that most people can handle about 7 chunks of information at a time. In 2004, psychologist Barry Schwartz introduced the paradox of choice concept, where having more options to choose from increases our anxiety and interferes with our ability to make decisions. When people are inundated with too much or badly presented data, they become unsure of how to move forward. When this happens, noise and confusion are introduced into the decision-making process, rather than creating a strong signal for improving decision-making. To resolve data days, once the data is trusted, it needs to be made digestible by the different users. The right data needs to be presented in the simplest format for the user need and at the right time. For example, we have standard symbology on an electronic navigation chart to allow VTS operators to visualize huge amount of data in a single and intuitive view. This data is not presented in a table as a list of targets with latitudes and longitudes. And so, to analysis paralysis. Typically, analysis paralysis occurs when someone overanalyzes or overthinks the data and it fails to arrive at a key insight, decision, or outcome. As operational environments embrace self-service analytics and data skills evolve, analysis paralysis will occur more frequently as the opportunity to explore large amounts of data become more decentralized, democratized, and become driven by a machine learning or artificial intelligence system. The data within a VTS system is going to increase as the number of sensors increase and decision support tools and systems generate additional data. Along the way, some will lose faith in the accuracy of the data. Others will be overwhelmed by the volume of data, and the way in which the resultant information is shared, and yet others may dive into the data looking for insights and never resurface. Mitigating and overcome these paralyzing traps is important to arriving at a clear decision-making using clean data and simple but accurate reporting tools to ensure the best decisions. One of the prime causes of analysis paralysis is the high volume of data and the number of data sources. The solution is to create trust in the data by ensuring that it's clean and validated and has a detailed audit trail. The data then needs to be made available to the operators using user-friendly tools and easy-to-understand reports and dashboards. This will lead to the valuable decisions, insights, and outcomes that support a safe, secure, efficient VTS operation that protects the environment. Thank you for your attention.
Thank you. Yeah, there was the third presentation, Mr. Arroyo.
That was very interesting. It's good to see Ernie progressing and bringing up to highlight this whole analysis paralysis. It's very interesting how the three presentations that have gone from the theoretical and continuing to do algorithm creations in China, Transys bringing a product to the market, close to bringing a product to the market, and then Ernie addressing the physical actual operator exchanges and providing the tools to the operator. So they kind of all meshed pretty well together, which was very nice, which wasn't by design, it just happened by happenstance, which is very good. My only, I guess, observation of this whole session that we've had here is that I wonder how much of this decision support tools will be able to be standardized, or how much of them will remain as proprietary products by particular manufacturers to go ahead to add to their product lines. It'll be interesting how we are able to take advantage of this technology, whether it'll have to be done on a manufacturer by manufacturer's basis, or it's something that can be shared and be deployed more widely as we move forward in this whole brand new world of providing additional decision support tools. And then we start adding artificial intelligence and machine learning. It's a very interesting decade ahead of us.
But you know what might be interesting, if this is a question you really like to post, then you can put it in the chat. There is on the platform, there's the post a question for everyone. So that would be a nice one to start a discussion about standardization of these tools.
We will do that.
Yeah, thank you. And thank you for being such a wonderful chair. And I hope you enjoy the rest of the day. Is it a warm day?
Yes, I have a full day ahead of me.
Yeah. Well, go ahead, make a walk outside, and then continue with your day. Thank you very much, Mr. Arroyo.
Thank you very much, everyone, and thank you to my presenters for some great presentations. Looking forward to the rest of the symposium. Thank you.
Thank you. Great for having you here. Yeah, like I said, this is such a great opportunity to post your question in on the platform so everybody can discuss with the topics that are on top of your mind. Well, this was the session of this afternoon. We have one more session to go, and it's about embracing e-navigation, and it will start at 1:20. So we'll be back in a couple of minutes, and I hope to see you there. Welcome back to the final and the fifth session of today, of the second day of IALA 2021. And this will be about embracing e-navigation. And our chair is Mr. Mahesh Alimchandani. He's the head of navigation safety at the Australian Maritime Safety Authority. He's a master mariner and has served on ocean-going cargo ships for over 14 years. And he's the recipient of an Australia Day Achievement Award in 2004 and the EMSA Chairman's Award in 2011. Let's see if he's already there. There you are. Welcome to the show.
G'day, Pauline. Good to be with you.
Very good to be with you. How are you doing?
Very well. Considering it's 11 p.m. here on this side of the world, I'm doing very well.
Okay, good. Well, I will give the floor to you so you can introduce the final speakers of today.
Thank you, Pauline, and hello, everyone. I trust you found these very diverse sessions and the topics presented so far to be thought-provoking. I certainly have. The theme of our symposium is Enhanced Maritime Safety and Efficiency by Connectivity. So let's just focus on the connectivity aspect of the theme. For this session, let's just take connectivity to mean the linking of ship and shore with relevant and timely information, just like the IHO Secretary General stressed yesterday. The IMO e-navigation strategy implementation plan that was updated in 2018 identifies 5 e-navigation solutions. Of these, 3 solutions deal with the efficient transfer of information between ship and shore. Therefore, quite clearly, the exchange of information is a key enabler for e-navigation. IMO's plan also identifies maritime services as the means of transferring such information electronically and in a harmonized manner. And an initial description of such maritime services has already been completed. So stated simply, maritime services refer to the provision and exchange of maritime-related data and information in a harmonized format. But there's much more to it than this simplistic definition. Our first speaker, Axel Hahn, will tell us more about maritime services. Axel is a full professor and leads the working group on system analysis and optimization at the Karl von Ossietzky University in Oldenburg. He is a board member of the Research Institute Office, Institute for Informatics, and leads the Department of Transportation in transition to become an Institute of Systems Engineering for future mobility of Germany's Research Center for Aeronautics and Space. At Office, Axel coordinates the research activities for maritime transport systems. His research addresses design, simulation, analysis of safety-critical, socio-technical systems in maritime transportation. A quick spoiler alert, I hope you all like pizza, because after this session, you may want to get some pizza. So I won't steal any more of Axel's thunder. Axel, the floor is yours. Over to you, please.
Yeah, thank you very much, Pauline and Mahesh. Thank you very much for the introduction, and thank you to all people around the world. Good morning, good day, good evening. And I hope at least you are hungry with pizza, because I, as chairman of a working group 1 on harmonization in the ENAV committee, were often asked, hey, can you explain all the stuff you're discussing that everybody can able to understand it? And that's the challenge I would like to address today. And so this example of pizza is credits go to Omar Fritz Eriksson, perhaps a lot of people know. And the deal here is really the question, what eating a pizza means for e-navigation. And we try to use this as an analogy to explain the concepts of the maritime services. And before we do that, let's have a look on the concepts we have in e-navigation. So what is e-navigation all about? As Mahesh already introduced, it's about, of course, to enhance the safety and security. And this is done often, of course, to make a better organization. A better organization needs data to be exchanged, ship to shore, shore to ship, ship to ship, and all that stuff. And this can be regarded, let me say, as a little bit as you all knew about everyday experience, because you're using your smartphone with dedicated apps to access services around the world, to do your daily business, to have fun, to do everything, to get the weather forecast as tomorrow. And we use then the question of ordering a pizza from a franchise company as an analogy for navigation. And to do so, to start that, I have brought this example here to handle with you. And so this is all about e-navigation. And what's about pizza? Yeah, pizza, the question here is with pizza is the following. Look, thinking about a hungry person wants to order a pizza fungi. Yeah, so it's like the mariner wants to retrieve information on traffic warnings from a VTS center, just to take this as an example. And this, especially pizza, can be ordered from a pizza store outlet, Tony's Pizzas in Hamburg. And in the analogy, the navigator wants to retrieve this information from a VTS center, Cuxhaven Elbe traffic, as a service provider for this. And of course, there has to be a coordination for that, and how to do that and provide all the definitions to do that is because Pizza Tony is part of a franchise company, and all the outlets are coordinated by a pizza store company. And this role has the IMO, and it defines for the maritime services providing this information from a VTS center, and requested the IALA as a domain coordinating body to provide this necessary information. So if we come back to the hungry person who wants to eat a pizza, and it is opening the pizza store menu and to see what informations and that provides the information what pizzas are offered and how pizza will be delivered. And of course, the telephone number and web page for a pizza store outlet, Tony's Pizza, people can retrieve information. So if you now look for the same thing in the e-navigation domain, so for the mariner, so what is available as an information can be taken from a maritime service number one, that is the information from VTS center specification. That is written by IALA that is to describe the operational perspective. So operational perspective means what the mariners can take from this service. What is the data, what is information provided for the mariners. So, and how the pizza will be delivered is something typically you're not anymore interested while sitting on the table having the pizza in front of you. But of course, how it gets to you is important, and this is described by something we named a technical service description. Yeah, and the telephone number, the web page to order that pay is in some kind of a service registry that is offering you the information how to access the VTS center Cuxhaven Elbe traffic to get this information. And to follow up with this example on my next slide here is, okay, now we have it. The pizza is then be delivered by bike, car, or can be picked up. So, and the maritime safety information provided to the mariner is sent, for instance, wireless by using a communication channel, for instance, VDES, or using LTE, or using Navtex, wherever you can name it. So, and the pizza itself is prepared by using a standard recipe. Yeah. And this recipe is something normally, it's not of any interest if you have pizza in front of you. Here, you're interested, it's good for you and it's tasteful. Yeah? So, but of course, there's something like a standard recipe to provide the information that is applied by the service provider, traffic information center, and it's structured by something we name a data model. So it's nothing more as a recipe. It has nothing to do with the special preparation of this individual piece of pizza, except that it provides the standard how to do it and explains how to do it. So it has to be, let me say, defined. And then the ingredients, so the dough, the fungi, the tomato, and the cheese are processed as defined in this recipe. And the data entry, so data is the raw pieces, bits and pieces sent to you that in the end, in your understanding, provide you with the information, is structured and expressed by the way it is described in the data model. So the data entities is the ingredients of the pizza, so the ingredients of the information delivered to you, and it is structured by for the pizza by the recipe, and for the data by the data model, how to explain it to you. Okay, now back to e-navigation. So what we have actually now is the following. If we look now back on e-navigation, how it is working. Yeah? So we have a navigation service, that is the gray box on the right side of my screen actually now. And we that is something the user sees. So the user sees that, and of course the whole thing is described as a maritime service. And if you have your mobile in your hand and you open just an app, you have an interface, a user interface to this client. Yeah, it could be a weather forecasting app, or it could be part of your actors on board of the vessel, parts of your integrated navigation system that is providing you with the information you can receive here. And this system, yeah, transparently is communicating by a dedicated means of communication, LTE, satellite communication, Wi-Fi, whatever you know that is available and what is defined, and get the information from a server. And this communication between the client server and the specification dealt with that interface are then specified by the technical service specification, and the information processed here. The data entities are structured in a way the data model is describing it. So what we have actually now here is, of course, the definition of the gray box. That is the maritime services, and here the IMO is providing a template, and IALA put all these description for this maritime service one into it, and there is a number of services. Actually, there is a list of 16. There's discussion of extending it. That is on the right side of my screen. But anyway, the maritime service specification is a formal description from the perspective of the user. So how it is for, what information is presented. And it's provided by the maritime service, by the IMO, and as coordinating body, especially for 1, 2, and 3, this information comes from the IALA to provide this information. Okay, let's go further on. As I said, the client is discussing and taking the information, exchanging data to a server, and this is defined by a technical realization. So we have a technical service inside the service, with server specification, how the client is discussing and exchanging this information transparently, invisible for the user. And this is described by a technical service, and we have a standard at IALA how to do that. This is for the tech guys, for the nerds like me. We read it, we use it to develop and program the client to provide the information to the mariners. So that is the things IT people typically do, reading this stuff and make them interoperable. And the next thing then is, of course, the data model. As I said, recipes, how to structure the data. It's also only information that the data is handled and represented in a way. The language, let me say, is defined as we use here English as at least what I name English as a communication means. I have a terminology, and all the things is, let me say, specified in the data model. And typically we try to use S100 as a standard data model everywhere to handle that. So now we have anything together, and what we can do now is we can set things together. And I have this, for instance, for the maritime services, and there's a specific maritime service for maritime safety information that has very, very similar aspects as maritime service number 1, and just have this as an example. So the maritime service is specified by the IMO, and there's a specific service for maritime safety information. It can retrieve information and present that in the actors, and it's exchanging information here by using a specific data model. It could be S100 124, but it's a specific part of the S100 family of all the specifications for data models, and can be reused here. So we have, in the end, the analogy here. We have a menu, what is information are presented from the maritime services. We have a way to how it is delivered. For instance, it is delivered by Wi-Fi or by the internet to an actors. And then how this is done is by the recipe. And this picture on the right side is part of the standard from the IMO, saying that the maritime service can use one or more technical services to retrieve the information. So, and they are specified in a technical service specification, and the data provided by these technical services are structured in a way the data model specifications, various subsets of S100 are defined there. Very important is that this is the only what you need to have that available. And of course, a maritime service, as it is described here in the gray box, can take information together from various services. So bring the things together, or it's just one app, like my weather app on my smartphone. Who knows? My smartphone app knows that the best weather reports coming from the German Weather Service and the Norwegian Weather Service, especially for my area, and is getting the information from one of these services. So that is, in a nutshell, the idea of maritime services. And of course, I hope you still have some hunger, and especially Mahesh, a good night dinner for you. I wish you a lot of fun with the pizza and wish you safe navigation with all the fun you have to enjoy your pizza. Thank you very much.
Thank you.
Thank you.
Thank you. Are we looking forward to some
Axel.
pizza?
And I think I certainly will after this session, but Pauline, in many Axel's presentation goes to the very heart of what e-navigation services are all about. And while Axel has laid the groundwork very well, there are many other strands to this: the choice of platforms for e-navigation services, cybersecurity, and these are all issues that IALA is dealing with in the eNav committee. So that's for a later session. And I always like examples. So I think Axel's pizza example will stay with us for a long time. But now to tell us a bit more about maritime services and to introduce the concept of something known as maritime connectivity platforms, I'd like to invite Thomas Christensen. In 2008, Thomas was the eNav project manager at the Danish Maritime Authority. And from 2011 to 2016, he led its e-navigation team. Thomas has also been involved in a number of eNav-related European Union projects like Efficiency, Axes, and he was the project manager for Efficiency 2. Thomas has also represented Denmark in e-navigation matters at IMO and IALA, and he has also organized the e-navigation underway series of international conferences since the first one in 2011 under the auspices of Denmark and IALA. More recently, Thomas has worked on the establishment of the Maritime Connectivity Platform Consortium as a governing body for the MCP. The consortium was established a year later, that's in 2019, and Thomas was elected as its Secretary General. Over to you, please, Thomas.
Thank you very much, Mahesh, and thank you very much to the organizers for having me here. It's very much a pleasure, and good morning, everybody. I think we need a new word because we are always meeting now online and from all time zones, and I think we need to say good morning now. So I will be talking about advances of the Maritime Connectivity Platform, or how to get a pizza part 2. And of course, as we know, e-navigation is all about exchange of information, and it's all about connectivity, as was clear from even the first presentations yesterday from Francis Zakaria and Mattia Jonas talking about connectivity. This is really what is important. And the exchange of information in a modern way using contemporary technology. And this was actually one of the emphases in Brian Wadsworth's first letter to the IMO back in 2005 that started the whole e-navigation process. The use of contemporary technology, where we know that the maritime domain have been lacking a little bit behind other domains. So, contemporary technology, what is that? And how is exchange of information done today? That is done through services. And what is services? Having been with the e-navigation community for many years, that has been a source of much confusion. Thankfully, Axel just made a very, very good presentation explaining this, where we have the maritime services on the high level that has been much discussed for many years. The maritime services describing things on a very high level, VTS services, hydrographic services, maritime safety information, but these maritime services do not facilitate the exchange of any digital information. For that, as Axel explained, we need to have the technical services. And in the description of the maritime services, we have placeholders for these technical services, and they are in the IMO descriptions called associated technical services. So they are technical services associated with the maritime services. And also it is important to note that these exchange of information through services is very much done computer to computer. Of course, in the end, there will be somebody navigating a ship or operating in VTS, or maybe only monitoring the operations of an autonomous vessel. But most of this information will be done between computers, machine to machine. So now I keep pressing the keyboard for next slide. That's not going to work, Thomas. So now a little bit promotion for some IALA guidelines here that Axel also mentioned briefly. We have guidelines for these technical services. Guideline 1128, the specification of e-navigation technical services. And we really need to get up to speed to make these technical services. There's been a lot of focus in the e-navigation world to work with the maritime services. There's been a lot of working on data modeling and the product specifications that contains the data models, which of course is super important, but we need more focus on the development of technical services. And also, we are going towards using the internet more and more. And that gives a lot of benefits, a lot of technology we can take down from the shelves and use when we use internet technology. And when we go into that area of using internet technology, the services that we're going to implement are called web services. And there's another guideline for that, which is more recent than the more general 1128. So this is a complementary guideline that explains how to create web services for exchange of S100 data. It's called 1157. So these guidelines are there to be used to create these technical services that will allow for this exchange of information in the maritime domain. And these guidelines, I would say, not only for IALA. Let's not reinvent the wheel again and again. I hope other organizations in the maritime domain will adopt these guidelines and use them, like we are seeing for the unique identifiers, maritime resource names that are being adopted by other organizations. That is very, very useful. But Thomas, you were supposed to talk about MCP, the Maritime Connectivity Platform. So how does that fit in here? Well, Axel mentioned a service registry. And in the pizza terminology, that was kind of the yellow pages where you would be able to find the phone number of the pizzeria. So we need a service registry. And in particular, when we go into the internet, we all know what's on the internet. There's a lot of things there. There's a lot of good actors, there's a lot of bad actors. We need to be able to find services, and a computer that needs to find a service, don't go to Google and try to find a specific service. It needs a reliable, organized service registry that it can request for services that it needs. So part of the MCP is a service registry for technical e-navigation services that can be found by anybody that needs them. And there are other challenges. There's also been talked a lot about security and cybersecurity and secure services. And there are several aspects of that. But one of the main aspects of that is trusted identities. And again, going into the internet, everybody is connected to everybody. And when a ship, for instance, enters a VTS area, it needs services in the future, possibly on the internet. It needs services for the VTS. How can the vessel be sure that the VTS and the services really are coming from that VTS center and not some evil meaning actor? And the same goes the other way, of course, when the ship needs to do reporting to the VTS, to other authorities, those receiving that information needs to know that it is in fact coming from the ship with the identity that it claims to be having. So that is another very important aspect of this information exchange that we need to achieve. So despair not, the MCP has recovered with an identity registry, providing trustworthy means of validation of entities, both of users, but maybe even more importantly by machines, so they can exchange information and know the identity, trusted identity by the both receiving and providing party. So the core components of the MCP is an identity registry for trusted and verifiable identities, a service registry for service discoverability, and it has another party trick up its sleeve, a messaging service for secure and reliable information exchange. That is important for vessels where, of course, connectivity is a little bit more challenging than on land. So the messaging service will mitigate some of the headaches that goes with connectivity at sea. So these are the different components of the MCP. So in order to make digitalization and make e-navigation, everybody needs to use the MCP. Well, where is it? Who's running it? Is it on a computer in Thomas's basement? Do we really want to use that, everybody? And the answer is no, you don't. And you don't have to, because the MCP is not the MCP. It is not one single system that everybody needs to use. It is actually either a decentralized system, a system with many different individual entities, or you could also see it as several different systems that are harmonized. So one decentralized system or different systems that are harmonized doesn't really matter, but it is important they're harmonized. Otherwise, we have not achieved anything. It needs to be harmonized in the same way that the data is harmonized, that the services are harmonized, the platform we use for service discoverability and authentication of identities also needs to be harmonized. So harmonization means we need to have some standards that describes that, so somebody needs to do that. So for that purpose, we have the Maritime Connectivity Platform Consortium. So as Mahesh mentioned, this consortium was established in 2019, and it is inspired by the World Wide Web Consortium that governs many of the standards that we use on the internet. So it has host members, which are the founding fathers of the consortium. They form a board, and everybody else can join as general or regular members. All the host members are non-profit organization, and everybody joins in a general assembly that is the highest body of the organization. And beneath, we have several working groups that are working on the exact standards and procedures that needs to be put in place in order to realize the MCP. And we also have an advisory board to get some input from important international organizations. So that's the MCP and a bit of a status of where we are today. The MCP has actually been underway for a long time, not quite as long as e-navigation, but since 2009, 10, something like that. Some of you would know that it was actually called the Maritime Cloud at that time. We needed to change the name because that was a lot of misconception, thinking that we were storing everything in a cloud solution, which we are not. So we changed this to the Maritime Connectivity Platform. So that is what we are really doing. We are facilitating connectivity. But testbed has been running since 2015. And the consortium, as mentioned, was established in February 2019, and there are now 25 members from many different countries of the consortium. And they're beginning to come operational MCP instances. The first ones were in Korea, operated by the Ministry of Ocean and Fisheries. And then we have one in Sweden, by the Navalink Consortium that was previously mentioned. The Navalink Consortium that was established by Wärtsilä, Saab, and Kongsberg in order to run an MCP instance. We now have FinTraffic from Finland, a governmentally owned organization that, among other things, run the VTS centers in Finland. They're in the process of setting up an MCP instance. And last week, I learned that Kronstadt from Russia has decided to set up an operational instance as part of a governmentally funded e-navigation program. And I believe the Russian authorities will be using that to provide e-navigation services from their side. So several instances is coming along. We are maturing the standards and everything is getting more robust and more mature. So I do believe that the MCP is beginning to position itself as a framework, a global framework for providing this connectivity, trusted, featuring information exchange among different stakeholders to support e-navigation and digitalization of the maritime domain at large, which was the intention of this platform from the beginning. Thank you very much.
Thank you. Thank you very much for your presentation. Interesting subject, Mr. Ali Manjani?
Yeah, that's right, Pauline. Look, as I said earlier on, the exchange of information from ship to shore features in 3 of the 5 IMO agreed e-navigation solutions. So I think the start of this symposium with these 2 pivotal presentations has been very well thought and put in by the program organizers, so full marks to them. But we're not finished as yet. We have one more speaker who will now shift focus to the ANAV architecture and its links to VTS, and will showcase an e-navigation roadmap, and Canada will show us how it's done. So to have that final presentation, I'd like to invite Jean-François Coutu. Mr. Coutu has been a software engineer for the Canadian Coast Guard for over 20 years and has been representing Canada at IALA for the last 12 years. He is now manager of the informatics department at the Canadian Coast Guard and leads the e-navigation and VTMIS areas. Good day, Jean-François, and over to you.
Thank you, Mahesh, and thank you to the organizers for allowing me this opportunity to present today. As you mentioned, my presentation will be about e-navigation architecture and VTS. So let's begin. So unfortunately for all of you pizza lovers, my presentation should not contain any reference to ordering a pizza at this time, at least not willingly. But we will be talking about a lot of technologies. As you've certainly heard in the last 2 days, there's a lot of technologies that are applicable to e-navigation. I've put some on the slide there. There are even more, like artificial intelligence and statistical analysis. And at the risk of failing miserably, I will attempt today to link them all together and create a single architecture where we can see all the different pieces fit together to reach a purpose. So this will be obviously a shore-based perspective, but the benefit of the proposed architecture for mariners should become quite clear as the presentation progresses. It's also worth noting that this is probably not the only way to make these pieces fit together, but over here in Canada, we believe it's a good starting point for anyone wanting to understand and undertake e-navigation. So let's begin first by identifying some objectives. So this is from a VTS point of view. What are the VTS objectives for e-navigation? It's not an extensive list, but the basic requirements that VTS might have for e-navigation. So obviously streamline and automate the process of vessel reporting, improve grounding, collision, striking avoidance, automate information exchange, and last but not least, enable an integrated image, which would show both the vessel traffic and factors that need to be considered, such as the water conditions, the meteorological information, and data from reliable sources if they're relevant to the situation. So with that, we're able to start our voyage down to the e-navigation architecture, but let's start with something that that we hold very dear. It's our partners and our stakeholders. What's important here to realize is that these partners will have different needs and they will have different tools, and they'll be looking for something different from e-navigation. So we need to keep that into consideration. Some might use specific tools and some might not. So on the upper part of the slide, you have your harbor master, your port actors. They may be using something called Port CDM, or Port Collaborative Decision-Making Tool, which they use to optimize their operations for logistics, for coordination. Just below that, we have the ship agent or a mariner, a pilot who's planning a voyage on shore. They might use a voyage planning tool that may have route optimization included in its capacity and its features. We also need to consider boaters, fishermen, coastal communities. They are players, important players as well. And last but not least, of course, the commercial shipping with the mariner on board, which may use different tools such as an ECDIS, an ECS, a PPU if they're a pilot. They might also have a different tool for ship reporting altogether. So all these partners and stakeholders have different tools, different needs, and they all want to interact. They all want to be part of e-navigation. From the Shore Authority perspective, in order to account for all these different needs and all these connectivity to all the various clients, we need to provide services, web services or portals to exchange the information with all of these partners. Notice here that the Maritime Connectivity Platform, the MCP, which was just introduced by Mr. Christensen, is identified here as part of a cloud solution to reach or to bridge the various clients with the various services that are provided by the Shore Authority. Moving forward to the next slide, we introduce here a bit of color in the very black and white presentation. So don't be startled by the deep color scheme here, but this is meant to highlight that we do recognize two different types of digital communication conduits for e-navigation. There's the general purpose digital communications like cellular 4G, 5G, or satellite low Earth orbit constellations. Those are public or commercial systems that are used by ships mostly to reach the public cloud or internet. But ships will also want to use some dedicated maritime digital communication methods through the Shore Authority network, like AIS, ASM functionality, VDE terrestrial, VDE satellite, NAVDAT. But hopefully, whatever mean or conduit is used to reach the Shore Authority services, the services that are provided come from the same source, the same core services based on international standards. And that is the subject of the next slide with some more color. Here we see that on the Shore Authority side, there is a need to have a repository of situational awareness and maritime safety information available as services, published services, to be more precise. All these services, these web services, and these portals that are available, they pull their information from standardized data sources, and that's very important. And that's where all the new standards are coming in, like S100, S200, and S400. It's very important that these services are available in these compatible format for distribution to all those partners. This is obviously a more shore-to-ship service where the authorities or the shore authorities provide situational awareness to the ships that are in their waters. The next slide introduces the single window. I'm sure you've heard of single window. We here believe that single window is a bit more of a bidirectional component of e-navigation, a more collaborative component. So single window will provide a way to exchange the data, and of particular importance in that exchange is the ship route plan, and of course, the reporting. We foresee that the single window will become the hub of the route and the voyage information exchange between shore and ship. And it should, because it is very important to have all the partners onshore and at sea synchronized on the route plans and the ETAs of ships that are voyaging in the waters domestically and internationally. And this slide is really where the magic happens. By providing your VTS, the ship's route plan in a standardized format, along with the situational awareness information, so you can see the bright yellow arrows there, so the ship route comes from the single window and the situational awareness comes from our e-navigation hub where all our information are available in S100 format. Then the VTS can compare the route plan with its sensor data like AIS and radar, and it can apply some rules which will help the operators do monitoring and surveillance and assistance, core services to the VTS. A VTS can then detect if a ship has a planned route or not. It can also detect if the ship suddenly slows down compared to its planned speed to meet its ETA, or if it leaves its planned route. The VTS can also detect possible collision risks by comparing routes from different vessels. It allows the shore authority to react and be proactive on managing potentially risky situations and avoid the risk becoming an incident. So this is the very important part of where VTS can really leverage e-navigation to improve and to attain its objectives. But plans do change. Sometimes the routes need to be updated because there's a delay at the arriving port, because the water level is lower than expected, so the tide window is smaller, or the air gap is sufficient under a specific bridge. These external factors can be considered to obtain a more accurate route plan for the ships. Shore authorities and stakeholders might take additional steps to ensure that real-time traffic is planned as accurately as possible, such as including under-keel clearance, traffic management, lock orders, pilotage rules, etc., in their route calculations before the route is sent to the VTS. That new, more accurate route can then be used by the VTS, but also updated to the single window, and then all stakeholders get the most accurate route calculated, giving everyone the most realistic, real-time, accurate status of ship movements, departures, and arrivals. And here you have it, the complete picture of the e-navigation architecture strategy for Canada. Now, I won't lie to you, this whole architecture will take a lot of work. So we have built a roadmap of our migration towards this architecture. Here it is for reference. We have progressed on many of those initiatives. Some are almost complete, some are just starting, and some are still at the design phase. So still a lot of work remains. On the left side, you will find a various level of digitalization involved in the various components. The higher it is, the more complex the project will be, but also the more benefits it will bring. If you look carefully at these levels, you will see that they also reflect the IMO's definition of e-navigation. So from bottom to top, to collect, integrate, exchange, present, and eventually enhanced. So this is our roadmap, our work plan for the next few years, and that's what will be busy or keep us busy for a number of years ahead. And that is the end of my presentation. So thank you very much for your attention. And if you have any question, if I can help in any way, please don't hesitate to contact me.
Thank you. Thank you very much. Also nice added value, this final presentation.
Indeed, Pauline. To me, it was quite remarkable listening to Jean-Francois's talk about how wide the eNav ecosystem is and the number of diverse partners and stakeholders that will benefit from when e-navigation changes from a concept now to an operational reality. We could also see clearly how maritime services described so nicely by Axel and Thomas fit into the big e-navigation architecture. So I think the three presentations have complemented each other quite well.
And this is a good moment that we have a discussion with each other, because we have three dial-in presenters here with us. They will appear on screen, and we have a question. So if we can manage to see the three presenters at the same time, that will be great. They are coming up right now, so we'll be seeing them. But now you have some nice... yeah, if you also have a question, of course, you can post them as well, Mr. Adam Chandani. We are waiting for them to come up in the screen.
Okay, so I can put it on to the general chat, or would you like me to ask a question now here of one of the speakers?
Yeah, you can do that right now while we're waiting for the speakers to come back. So if you have a question, you can do that, and they will probably hear it and respond to it.
Okay, one for Jean-Francois. Can you tell us, or what do you think would be the upcoming technology that you think will have impact on e-navigation?
Okay. Okay.
Yes, thank you for the question. We've spoken so much about connectivity these last 2 days. My opinion is obviously a technology that will have a big impact on connectivity, and one that I'm keeping track of is satellite low Earth orbit constellation. The promise of having large bandwidth at very affordable prices available globally, even at the poles for the shipping industry, I think will revolutionize e-navigation and transport, maritime transport as a whole, and pave the way for more advanced things such as MAS and autonomous ships. I think that's the technology that I'm most eager to see being available to all.
Yeah, and we also have a question for Mr. Christensen. Is the Maritime Connectivity Platform Consortium a sufficiently robust organization to deliver the global maritime communication framework? I think that's an interesting question also for you, for the other presenters to react to. Go ahead.
Right, thank you. Well, obviously, the MCP consortium is not an organization like IALA or IMO or IHO that has been around for decades. But I think it is important to note that if, heaven forbid, that the consortium disappeared tomorrow, the MCP would not disappear. The MCP would be running with the different instances that are actually running concrete instances of the MCP, much as if the World Wide Web Consortium disappeared tomorrow. That wouldn't make the internet stop working. Of course, some organizations need to reach out to each other to make sure that the harmonization would stay in place and we would still be running with the same standards. So somebody needs to do something, but it wouldn't mean that that the MCP would stop working. So that is an important point in this context, I think.
Anyone else who would like to react to Mr. Christensen?
Just what Thomas said, this definitely is, you have to regard it as some kind of service organization. It is providing the standards and provide help to define that. That is, for instance, helping IALA to develop a guideline 1168 and others. And it is providing input, for instance, to IAC and other standardization bodies as well in parallel. So regard this as a supportive activity. And it's a club. It's a association. It's a fanboy club supporting that and bringing this further on. It's just a way to organize to develop a specification. It's open. It's open to everybody. It's free of charge, and it's just a big thing undertaking to bring together German force. And especially, you have to thank to Thomas and especially to South Korea to support that and sponsor it financially wise to bring this further on. I think that's a big thing, and but just regard this as an organization form to define the standards necessary to do so, so that then Jean-François has something to take and to implement and run on his behalf and his responsibility. It's just a support.
And what is needed to become maybe as big as the other organizations that have been there for decades? What is needed at this point to become a robust organization?
Thomas?
Well, maybe that's not the aim. I mean, we've even talked about the possibility of the MCP consortium to be assimilated to another existing organization. That may also be the future. Basically, we just want to see this become a reality. The goal is not to create a big organization around it. We just want to see the MCP become a reality and support e-navigation and digitalization in the maritime domain.
Nice, thank you. We also have a question for Mr. Goutu. What upcoming technology do you think will have a significant impact on e-navigation?
Yes, thank you. As I mentioned, I think communication is the key here, and we're certainly monitoring a lot of various communication technology. I think VDES is definitely promising. And as I've mentioned, satellite LEO, low Earth orbit constellation is at the top of my mind. And if I could name a third one, cellular 5G, I think shows a lot of promise as well for the maritime world.
Okay. Is there anything that you would like to add, Mr. Alimchandani?
Yeah, thanks, Pauline. Look, just a quick one for Axel. For the benefit of all attendees, Axel chairs one of the working groups at the IALA's Information Services and Communications, or what was previously known as the ENAV Committee. Axel, can you tell us very briefly, or just list for us some of the work that the working group is doing in developing guidance? For example, we've done one on the platforms for maritime services. And can you give us some examples of the kind of work IALA is doing to progress maritime services?
Yeah, so we are pretty much in the machine room of everything. And at IALA and in other organizations, we have experts. We have experts for BTS, we have experts for AIDS navigation, we have experts for engineering activities on these issues. And the NAVI committee, we try to provide a broad support for that, the standard necessary to develop the services in the specific domain. So It provides the templates. It provides the harmonization of that. And then this is taken by the experts to develop them the specific services, for instance, for BTS information and all that stuff. So we try to do the organization, the harmonization of it. Just to give you an example, we developed the concept of a unique, universal identification mechanism, so that we have a unique way to make reference to each entity in the world of the e-navigation. We name the Maritime Resource Numbering, MRN. And something like that, that is the support we are doing here. And support then the other activities to bring in the domain expertise, to apply that and develop necessary services or service specifications. Yeah.
Thank you.
Just to harmonize it.
Great. And before we're wrapping up, I would like to know what is it that you're hoping to get out of this 14th symposium? And if you mention that, what do you need for that? Let's start at Mr. Coutu.
Well, for me, those events are always full of exchange of ideas and information between what's going on one side of the planet and what's going on the other side. It's a source of inspiration, really, in our work, trying to put all these ideas together and come up with new ideas. It's really a creativity exercise for me personally.
And is there something specific that you would like to mention or that you need to get the most out of it?
Well, I've seen some presentation already that I found extremely interesting. I'll mention the one from Wärtsilä, where their algorithm can detect behavior and then try to alert the operators on a risky situation. I thought that was revolutionary, and it's a little bit what we had in mind also in our architecture, but not to that level, to that same level. So that's always fun to see same or similar ideas taken to different levels.
Yeah. Mr. Thomas Christensen?
Yes, of course, my focus is on the MCP. So such a symposium here that provides me input on what is going on in the digitalization process in many different areas. And of course, that is input to how we develop further the MCP, because we want that to be a platform to support all these different services and solutions. So this is very important for us to be able to follow what is going on and which direction development is being done.
Yeah, and I really liked your opening that you said good morning. But then we're missing the afternoon. So I was thinking, why not good noon night or good after night? Then we have all the parts, right?
Yeah, right.
And for you, Mr. Hahn?
Yes, I see this whole digitalization stuff as a big challenge. And as a big challenge, it has come also with the potential of a disruptive evolution. And we have to face that. And we have to see the challenge and to make the best out of it and make a brighter and more safer navigation of the future. And I think we have a lot of mechanisms on hand to do so. And I think we have to come together. And this is one contribution here we have with this symposium, to bring people together, to work on that and to find a brighter vision and to change navigation. I think there will be a change as in any other domain of the world by digitalization. We have to make the best out of it and we have the power to do so.
Great. Well, I hope that there will be some inspiration, answers, solutions for the challenging time that we are facing, of course. Is there anything that you would like to say before we wrap up with the guest, Mr. Alimjanani?
No, I think in different words, the three presenters have sort of captured what I was going to say anyway, so I won't repeat it. The only thing I'd like to do is thank the three presenters for their excellent presentations. And like them, I look forward to the rest of the program for the next 3 days. Thank you.
And thank you very much for being such a wonderful chair this session. I thought that you were going to say, and I'm looking forward to the pizza, because that's right now, that's time for pizza right now. So thank you very much for being with us. And thank you, gentlemen, for being with us. And I don't know exactly what time you're in, but I hope that it's time for pizza for all of you. Thank you very much and have a wonderful
See you later.
See you later. Bye-bye.
Thank you, Pauline. Thank you.
Thank you.
Have a beer with it. Bye.
Yeah, we are wrapping up this final session on day 2. And tomorrow we start again at 11 UTC time, Wednesday, April 14. But we have a side event that starts a little bit earlier, 1 hour early, between 10 and 11 UTC. It is the webinar Digital at Sea. And we have 4 guests, Mr. Francis Zacharias, Secretary General IALA, Mr. Andreas Noordset, Director General DMA, Mr. Sanbo Hong, Director of Korea MOF, and Mr. Ed Wendland, President of RTCM. You will see a link in the chat that will appear today, but also tomorrow. So you can click on the link and then you're in this session. So please enjoy. And like I said, there's a lot happening on the platform, so go check it out. There will be a new poll that I will refer to tomorrow morning or afternoon or night, depending on where you are in the world. Thank you very much for joining us, and we'll be back tomorrow.